Good morning, everyone. Our team, consisting of Deepak, Reddy, myself, Chirag, Rudresh, and Adithya ASS, are going to be presenting our paper titled Multilingual Speech Recognition Methods Using Deep Learning and Cosine Similarity. A brief outline and what we will be presenting to you today is an introduction to our problem statement and the scope of our project, the summary of requirements, dependencies for our project design, research and conclusion on current existing solutions on multilingual speech recognition, a detailed description of our proposed design and the module and their implementation with the demonstration. We will also talk about the testing plan and strategies and discuss the obtained results. We will then conclude with our inference and future work for our project. Let me start off by stating the problem statement. Multilingual regional speech recognition. Multilingual sentences include a combination of two different languages in a single query. There is a tendency for people to speak in a mixture of languages, and the recognition and translation of these multilingual sentences is a problem that needs to be explored further in detail to develop an accurate and fast solution. Our proposed solution to tackle this problem is to develop a deep learning model that takes an audio multilingual speech navigation query as an input and recognizes each word in the sentence by converting it from audio to text query. The novelty approach that we have used in this speech recognition method is combination of the use of a word predictor model to reduce the search corpus of the speech recognition DL model, and thus increasing the accuracy of the words recognized. The scope of our project includes taking an audio query consisting of a combination of English and a regional language, which we have chosen as Kannada. This voice recording is then converted to a wave format, and the output of the next word predictor is given to the recognition model for accurate results. Some of the major requirements and the dependencies of our project include a dataset consisting of both audio and textual queries for the training of the model. The audio query should be in a wave format. The audio recording must contain sufficient gap between each word utterance. The input query should be a simple command or a single sentence, which is not too long and difficult to comprehend. And the speech query should be less than 10 seconds. It is also expected that the user pronounces words correctly. The major Python dependencies for our project are NumPy, Pandas, Matplotlib, and IPython.display for the visualization of wave files, Librosa, Seaborn, TensorFlow, Pickle, and audio segment. Now, Adithya will talk about our research on existing solutions.
Oh, hello everyone. Good morning. So currently, these are the top 5 speech recognition softwares: Google Speech API, which is using Google Translate; IBM Watson API. We have Speech API and Speech to Text API as well. These are Python libraries, and the Rev.ai API. As you know, in Google Translate, you can choose a language, and when we choose the current language as English, when let's say any other foreign word is spoken, it is mapped to the closest sounding English language. For example, when the input speech is how to go to Shale, where Shale means school in Kannada, and all these other English words are recognized properly. However, Shale is mapped to the closest sounding English word, which is Charlotte. Now, coming to Google Translate API, there is a dependency that we need to input the languages present in the input query. And as you can see, that is not really ideal in the real world scenario. So the inbuilt Python module doesn't work as good as Google Translate, and here you can see the input file, which was originally mg road reach agake yestu time agote, and the result that you see there, it isn't as same as what it isn't like. Most of the words are not as expected. And coming to the detecting of languages presenting multilingual sentence, we use Python libraries for this as well. And for this, even though English words were recognized, the other words which are present in other languages, it failed to recognize these words. Deepak will now go through the design description of our project.
So the approach that we came up with can be broadly divided into 4 modules. So first is the splitting of the sentence module, then the pre-processing module, then the next word predictor module, then the deep learning module. Now let's move on to the high-level workflow and then later look into each module in detail. So the input multilingual sentence that needs to be translated is first extracted into a wave format. The wave format is then passed to the splitting module, where the wave file is splitted up into multiple smaller wave files, which we call as a chunk, where each chunk would represent each word uttered in the input sentence. For example, if the input sentence contains 6 words, the splitting module will return 6 smaller chunks, where each chunk would represent one word from the input sentence. These chunks are then passed to the pre-processing module, where necessary pre-processing is done. Then these pre-processed chunks are passed to the deep learning module that uses a deep learning model to map the audio to the text and generate the corresponding sentence. So the accuracy of the speech-to-text module is further increased by using a next word prediction model. So this model takes the sentence generated so far as the input and then returns the set of words that may possibly occur as the next word. The deep learning module takes this set of next words to reduce the search space and then make a better prediction. After the next word is predicted, again the sentence generated so far is taken as the input by the next word prediction model. And then again the set of next possible words are returned. This keeps on happening until all the chunks are mapped to a word and the sentence is fully generated. Since this deep learning model was comparatively slow, we also explored an alternative approach which is faster and is based on the similarity of the waveform of the words. However, the accuracy of the prediction was less compared to the deep learning models. Before we discuss each module in detail, we look into the data that is used for training. So firstly, we have generated 384 commonly spoken English queries. And then for each of these English queries, we have generated all the possible multilingual sentences. Here, the multilingual sentence is composed of English and Kannada. Most commonly spoken words are picked from these sentences and are recorded multiple times for training. The text sentences are used for training the next word predictor module, and the word recordings are used for training the deep learning module, which as we discussed maps the input audio to a word. When we say the input audio is used for training, the input audio isn't directly used. Rather, it's pre-processed and MFCC features are extracted. MFCC stands for Merrill Frequency Capsule Coefficients, which is the state-of-the-art feature extraction methods for audio processing. Hence, here the MFCC feature vector of size 40 is used as input against the label, which is nothing but the corresponding word here. Now, Adithya will deep dive into the implementation detail of the pre-processing module.
We felt pre-processing was necessary since there might be different users who can speak with different tone of the data, and also each word can be spoken at different speeds. So we split this pre-processing into 3 different steps. One is the normalized step, where we try to convert all the audio files into an array, and the value of this array will be between -1 to 1. That is what you see in this normalized function. And next is the trim process, where we try to remove the silence in the in the starting of the audio file and to the end of the audio file. And coming to speed change is, since the words can be spoken, the same words can be spoken at different speeds by different people. This is after comparing various values, we came to a target length of 20,000 for the length of the array. Like when we convert the audio file into an array, we make sure that the length of the array remains at 20,000. By doing so, we control the speed of the array, and such that all of our training data set will also be uniform. We can see the code implementation of it as well.
1 second.
I think your screen.
Yeah.
So this is the code implementation where we have the pre-processed file, and we do have different functions. If you can see, we can see a sample data set. This is the first fully splitted. I believe we can't hear because the data you're headed. So this is the entire full sentence, Nanna next turn yenu, out of which 2 words are from Kannada. And original, this particular folder is where we split, which the splitting module is happened here, where which will be explained by Deepak further. And each word is splitted. Can you play it? So this is the first word, Nanna. This is the second word, next, and similarly the other 2 words are also splitted. And coming to scaled is where we try to normalize between -1 to 1, since the audio volume will be different for different users. A couple of examples here. You can see that the word is barely audible for Nanna. If you show the next example as well, please. This is for next, and you can see that it is like really less audible, such that, so this has happened because we've normalized everything between -1 to 1. And coming to speed change, click, yeah. So you can see that the time limit is like almost at 0 seconds from 1. So the speed has also been increased in this case. So there are certain cases where if the user speaks slowly, then the speed slowly than our target value, it will be increased. However, if they speak fast, the speed will be reduced. And again, coming back to the trim state is where we trim the initial first and the end silence and the starting silence. So the differences are really like, it's not possible to hear with your naked ears, but when we switch to machine learning where we use arrays, this does make a lot of difference. Now, Deepak will go to the splitting of sentence module.
Yeah. So now coming to the splitting module, as you can see, here is a sample visualization of the WAV file for the sentence, which is multilingual, spoken by one of us. So the sentence contains 6 words, and you can see there are 6 different peaks here, which are clearly visible. So this would be the each word utterance, and then you can observe there is a period of interval where the amplitude is low. So these could be the points at which we can split the WAV file to get the waveform for each different word. But the problem is the minimas aren't clearly defined, and we don't have fixed point at which we can split. So what we did was we smoothened this WAV file by taking moving average at 10,000 array size, and after taking the moving average again, and after visualization, you can see in the bottom picture with the moving average, you can see the minimas are clearly defined now, and we have a distinct point at which we can split the WAV file. Now we'll see the code once. So the splitting module will take in the file name, which is nothing but the full word or a full sentence recording, and then it is loaded using the Librosa library. And then here you can see the waveform for a sentence that contained 8 words. And there are few words which are comparatively lengthier and could have more than one peak, but the distance between the peaks could be smaller than between the words. So, and you can see even the 6th word has many different peaks that is unique. So the way to differentiate between words is the difference between the highs and lows and difference between the peaks that exist in the same word. So since we don't have a clear point at which we can divide this wave file, we then, as I said, we have smoothened it, and after smoothing it, we got a graph something like this, and you can see the minimas here, and these could be the points at which we can split. So after splitting, this would determine the indexes at which the splitting can happen. So this is nothing but an array at which where each index is nothing but the amplitude. So the whole processing is done based on the amplitude. Now Chirag will talk you through the word predictor module.
Next, we see the architecture and the summary of the word predictor model, which uses the long short-term memory to take input text and predict the 5 next possible words. The first step includes pre-processing the input text by converting the sentences all into a lowercase. We then split the sentence into a sequence for training, and the sequence length is determined by us, which is a length of 4. And each unique word in the vocabulary is tagged with a token, and the sequences are converted to their respective tokenized representation. The LSTM model is then trained on this sequence of tokens, and the next possible 5 words are generated in the token form, which are then mapped to the corresponding word text. We'll take a look at the code now. Yes, so here are the Python dependencies for the LSTM model. First, we pre-process the data by converting all the words into a lowercase. We then define a token training length as 4, where each sequence is then divided into 4 words, and then these sequences are sent to the word for model for training. We then tokenize each word, which is assigning each unique word in the vocabulary to a single integer. And for the recognition of the starting and the ending of the sentence, we have tagged S and E, which represents the starting of a sentence and the ending of the sentence for the context. So now we see a representation of the tokenized sequences, which are then fed into the LSTM model. So we have three different LSTM word predictor models, model 1, model 2, and model 3. Model 1 takes a single word input and predicts the next possible outputs. Model 2 takes two word inputs and predicts the next possible 5 words. And model 3 takes the 3 prior occurring words and then predicts the next possible 5 words. So depending on the number of words that are given as the input, the appropriate model is selected and the appropriate next 5 words are generated. So we see in the result over here that we are given 3 words, S, which is the starting index of a sentence, and PES, college, is given as the input. So the model 3 is taken into consideration, where they have taken 3 input words and the next 5 possible words are generated, which are some, the, near, to, and hattirada. So on exploring, we have found, and on results, we have testing this result, we have found that the next possible word in the sequence for PES college is in fact existing in one of these 5 possible words.
Now we look into the deep learning model. So as I've said, this deep learning model takes in the feature vector generated by the MFCC feature extraction method. So this model sees it as a classification problem, and when it receives a set of words from the next word predictor, since it's seen as a classification problem, it would classify one of those set of words as the next word. So this model contains one input layer, 3 hidden layers, and a final output layer. The input layer consists of 40 neurons, which is same as the vector size, same as the feature vector size. And then the first hidden layer would contain 100 neurons, the second hidden layer contains 200, and the third hidden layer contains 100, all activated by the ReLU activation function, and the final output layer is activated by the softmax. Now we'll take a look into the code. So this code includes all the previous modules that I have discussed, such as the splitting module, and the pre-process module, then the word predictor, and then the actual predict function, which contains the code for the neural network. And you can see here we have run it for a sample sentence, which is what are some uttama hattirada stalagal to visit, where the 3 words in between are from Kannada and the rest is from English. So initially the sentence is not yet generated. So the deep learning model would ask the next word predictor, what could be my first set of possible words? So the next word predictor returned these 3 words, which could be the starting of the sentence. So the deep learning model selected, after classification, training and classification, is selected that what could be the first possible word. So now the first word is predicted as what. Now this is the sentence that is predicted so far. So this sentence, which is now only of one word, is sent to the next word predictor module, and it returned a set of words that could appear in the that could be the second word in the sentence. So the set of possible words are, is, and does, and the deep learning module again trained on this, and since this is a classification problem, and selected the word are as the next word. Now the sentence generated so far is what are, and the sentence generated so far, which is what are, is now again passed to the next word predictor, and then it returns the set of possible next third word. So this keeps on happening until all the words are classified and the full sentence generated. And the predicted sentence is what are hattirada uttama hattirada salagal to visit, and which only differs by one word out of all the 8 words. So 7 words are predicted correctly in the sentence. Now Adithya will talk about the alternative faster approach.
Since the deep learning model was taking a bit of time, we tried to come up with another approach where we try to compare between the similarity of the words with the help of cosine similarity. And here, what we do is we try to take the array values and try to find the cosine similarity between our training data set and the test input that we get. And based on that, we now take there is one approach where we take the top 20 highest similarity and count the frequency of each individual classes, where each class is nothing but a predicted is the actual word, possible word. And the next approach is where we take average similarity of all the classes that is present, and in that give the next predicted word as the one which has the highest average similarity. Now, if we see the implementation of it. As used before, we do use the word predictor model, the splitting model, and even the pre-process model. And if we just go to the end to see the output, so the actual sentence is Nana next turn Yenu. And the first classes that from the word predictor model are of the first 7 classes. And in the next dictionary, you can find the average similarity of each individual class that is sorted based on from the highest average to the least average. And you can see that the first word is Nana. This is the first approach. And the second approach is where we count the frequency of these classes by taking the top 20 similarity. And you can see that Nana has appeared 18 times, whereas R has appeared only 2 times. For this, with the help of word predictor, we add weights to it, being like if R comes first compared to Nana, R will have more weights, whereas Nana will have less weights, and we multiply this weights with the frequency, and whichever comes the highest value, that we show as the next predicted word. And in the next case, you can see average similarity word is Nana, whereas for frequency, the predicted word is also Nana. This is again repeated for all the next inputs words that we get. And finally, in this case, you can see that Nana next turn Yenu in both the cases for average similarity predicted and even the frequency sentence, and the actual sentence is also Nana next turn Yenu. This is again repeated for all the different data set, and the accuracy is noted for each. We'll now walk you through the test plan and strategies for each individual models that we've presented now. Coming to the splitting of modules, what we did is we ran through all the test cases individually for the splitting module, and then compared the output to check manually if those words have been splitted accordingly. And we found out the accuracy by just counting the number of words that has been actually splitted properly to the ones that have not been splitted. Now, coming to the word predictor, we took the model's accuracy that the model shows, and as well we tried to see the output results and to see if those results were as expected. For DL model, the ratio of correctly predicted words to the total number of words that is present was calculated, and even the accuracy of the model for each individual word was also noted. Coming to the cosine similarity model, for the frequency of top 20, as I said before, the first frequency of top 20 classes was taken and the weights were also added to it. And similarly with the DL model, we then later compared to the average of like the total number of correctly predicted words divided by total number of words that is present. The similarity for the highest similarity, we took the highest average similarity of the class and then showed that as the next predicted word. And similarly, accuracy was found again by using the same strategy as mentioned in the other 2 methods.
Now coming to the results of the splitting module, we have run the splitting module for 30 different sentences that we have recorded manually. So out of those 30 sentences, 28 of those sentences were splitted correctly, and the incorrectly splitted the 2 sentences were re-recorded with sufficient gap between the words, and then those 2 were also splitted correctly. As you can see, the text sentence has 4 words and the predicted number of words are 4. And if you have after we checked the indexes at which they were splitted, they were proper. So each chunk would represent the full word properly. Now Chirag will talk about the results of the word prediction model.
For the word predictor, the model was trained on the in-house multilingual textual dataset, and it gave an accuracy of 90%. And when tested on multilingual textual queries, the output generated, which were the 5 possible words, it was observed that the next word in the sentence was in fact present in one of the 5 words. This model thus reduces the search corpus of the recognition DL model, which now does not have to traverse through the entire vocabulary to find what the word has been predicted as.
Now coming to the results of the deep learning model. So during the training of the model accuracy for the test split is given as 85%. But then after we check the word-to-word matching divided by the total number of words that we tested, the prediction accuracy came out to be 71%.
Coming to the cosine similarity model, as we said before, the accuracy got reduced compared to the DL model. However, the speed of execution of it was much quicker. And the average accuracy was 0.59% when we took the highest average similarity for each class. And when it was noted to be 0.64 when we took the frequency of top 20 most similar recordings. Now, finally concluding, we did check with the accuracy with the current existing model for our data set. And we use CMU Sphinx, which is a hidden Markov model. And we trained this using phonemes. We added phonemes for this and trained this with our data set. And the accuracy came out to be 57%. Similarly, we did it with the help of neural network, and that measure came out to be 64%. We used our test data set with the Google Translate. And if we see only the Kannada words recognition, where we find the number of Kannada words that is actually predicted correctly to the total number of Kannada words present, the accuracy came out to be 35.4%. For our deep learning model, which we built with the help of MSCC feature, for the entire model, it came out to be 71%. Whereas if we took only words, Kannada words recognition, the accuracy came out to be 66.6%.
Our proposed method does indeed give good results as seen before, but there are a few improvements that can be made to increase the accuracy of the recognition further. We can increase the data set, both audio and text, to include more variation in voices such as different age groups, genders, and include variation in the noise level as well. The similarity approach can be improved by using the similarity index comparison between the spectrograms of the generated wave files instead of the proposed comparison of the two waveforms. Furthermore, the scope of the project can be increased to include capturing the context of the words being predicted and their parts of speech by leveraging the use of various language features. Thank you.